All right, here we go, team. Have fun.
We'll go ahead and start the presentation with Austin Pearson. He's been with Purdue Extension for a few years now in a couple different counties, in central Indiana the whole time. And he's been, his training is actually in agricultural meteorology, so he's been working on these kind of things for quite some time. Take it away.
Thanks, Hans. I'm going to go ahead and turn off my video here so we can try to reduce some of the bandwidth that we have going on here. So as Hans said, I did do my bachelor's and master's in applied meteorology in the agronomy department at Purdue. And so we do have a climatology program that I focus a lot of time on. I did work for the Indiana State Climate Office, Hans. So I did work for that my sophomore, junior, and senior year. So I had quite a bit of exposure with looking at data, understanding backgrounds, and how to process, look at different data sources. But today we're going to be talking about back to the basics. And I know this is probably going to be a bit of a review for a lot of you, but some of you, this might be the first time that you've seen anything with this. So, just hang on. I mean, if you've seen it, we apologize, but it's always good to have a refresher for everything with that. So, thanks again for joining our series today, and we're going to go ahead and get started. So, just quickly going through a review here. The Earth's climate is a dynamic and complex system. Okay, and you see here on this slide that there are several different factors that go into the Earth's climate system. So you have the sun, you have the atmosphere, the clouds, the oceans, land, ice, and humans. So we're all part of the same spaceship, essentially floating through space. The picture like this shows how scientists actually understand the Earth as a system. So there are many factors that influence Earth's climate system, which, like I said, include the sun, the oceans, humans, clouds, land, and ice. All these components change at different rates. So the atmosphere, it actually adjusts to the conditions at the Earth's surface. So like an ocean temperature or ice cover within a few hours to days. But if you start talking about like the currents that are in the deep sea, they require several hundreds of years to actually change conditions. Climates also vary by different regions, so as a result of local differences in how these factors actually interact. So if you change one piece of this actual puzzle piece that goes, or one little puzzle piece of this entire picture here, the climate is actually going to reflect differently compared to different places throughout the globe. So that's just kind of what's going on here. When you start looking at human influences, and we'll start getting more into human influences later in the presentation, but you'll see how we have an impact on that, the way ice melts and what that does to the overall energy budget of the Earth. So there's a lot of different feedback processes that go on when you're talking about Earth's climate system. So it's not a very simple system to put on and take measurements of everything, but climate scientists do their best to try to make sense of it all. First, I know Melissa did talk about weather versus climate the other day, but I wanted to hit on this again. Oftentimes in our conversations, we use the terms weather and climate quite interchangeably. Is weather really the same as climate? No, not really. But weather is actually the mix of events that happen each day in our atmosphere. So even though there's only one atmosphere on the Earth, the weather isn't the same all around the world. So weather changes over minutes, hours, days, and weeks, so a much shorter time scale compared to what we talk about with climate. Most weather happens in the part of the Earth's atmosphere that is closest to the ground, and that's primarily in the troposphere. So that's all the way up to the tropopause. It's really just kind of where a lot of that weather does happen. Several variables do change rapidly. So when we are talking about weather, we talk about air pressure. We also talk about temperature, humidity, and a lot of people don't necessarily know what humidity is, but it's basically the amount of water that's in the air, or water vapor that's in the air. The more humid, the more water that's actually available with that. wind speed and direction, and other variables that go into forming the weather. When you start combining all these different items, and one little thing could be off or change, but you're ultimately changing the weather of that particular location and time. So that's something to consider when you're talking about weather. Climate, when you're actually referring to climate here, it's the average of weather for a particular place over a long period of time. So the basic difference between weather and climate is just simply put, the period of time. Different regions can have different climates. So you can have microclimates set up. So if you're up near Lake Michigan, and especially if you get lake effect snows, you can have a microclimate up there where you get an excessive amount of snow compared to your neighbors to the west or east. So that's something that definitely takes place when you're looking at those areas. So to describe the climate of a place, we might say that the temperatures are like during different seasons, how windy it usually is, or how much rain or snow typically falls throughout a given year. Now, when scientists talk about climate, they're often looking at averages of precipitation, temperature, humidity, sunshine, wind, and other measures of weather that occur over a long period of time in a particular place. So in many cases, that may look like these average over 30 years. And a lot of times climatologists and meteorologists like to look at these and they call them climate normals. So we like to use those to actually describe the weather, whether summers are hot, how humid they are, or whether winters are cold and how snowy they are for a particular place. I find this quote kind of amazing, but Mark Twain, back before computers existed and all that stuff, he did say that climate is what we expect and weather is what we get. So it's kind of amazing that you see, that far back in time, they're able to gather that information and determine that. Another way to looking at the difference between weather and climate is weather actually tells you what to wear each day, but climate actually dictates what types of clothes you have in your closet. So, I mean, just trying to distinguish the differences between those. Now, we're going to kind of talk about some other common terms that folks like to use. And I know when you use global warming, climate change, I mean, it's a highly political topic. But when you look at trying to define both terms, I mean, is global warming the same as climate change? Well, not really exactly. Global warming represents only temperature increase on a global scale, whereas climate change actually refers to changes in climate variables such as precipitation, snow, wind patterns, sea level, and extreme events in addition to temperature changes. Also, the term climate change doesn't only talk about changes on a global scale, but also on a regional scale. So climate change is a more complete term as opposed to global warming, and that is the reason why it is used more often in the scientific community. So you can kind of see that on this slide here. When we talk about climate variability, we oftentimes talk about short-term variability in climate, and it's oftentimes confused with climate change. For example, so if you have 1 or 2 consecutive rough winters, that may not individually prove anything about global temperature warming. Similarly, if you have a severe drought conditions or severe flooding for a few years, that's really not sufficient enough to make any statements on climate change. Climate variability represents the changes in the mean state of climate events on a short temporal and spatial scale compared to climate change. Single year climate extremes don't individually correspond to climate change. However, collective evidence over a long period of time do. So you can kind of see on this overall scale that we did plot a trend line, and you can see that the trend for that between 1895 to 2012, there was about an increase about a 1.5 degrees Fahrenheit for that. So, it's really important, and you hear a lot of folks try to debate the topic of climate change, and they say, well, climate change is really prevalent this year, huh? We've got really wet springs, flooded our planting out, and really caused some issues for a lot of folks. But yeah, and that's definitely that's definitely climate change, right? Well, it might be, but we just remember when we talk about climate change, we're talking about those longer time periods, for instance. So when we look at causes of climate change, we can divide that up into natural causes and human causes. The climate at any given location seems to be relatively stable, but it is ever changing because of its dynamic nature and many components. And so we talked about the natural causes and then also the human or anthropogenic causes. So for natural causes, any given natural activity that emits greenhouse gases into the atmosphere are categorized as these natural causes. So examples here of those are evapotranspiration from water bodies. So you can see the evapotranspiration of water bodies going up and forming clouds. And then you get transpiration of plants respiring into the atmosphere and providing water vapor up into the air. I mean, those are natural processes. Another example is wetlands, which are primary source of methane gas emission due to the decomposition process. Or if you have permafrost that's melting, that's something that's natural, that's actually releasing the greenhouse gases into the atmosphere. Volcanic eruption is another example of a natural cause. When volcanoes erupt, aerosol particles spread into the atmosphere and creates a reflective shield. That would ultimately prevent solar radiation from coming inwards to the earth, so you might get a little bit of cooling associated with that. That's primarily over a shorter period of time, but other potential greenhouse gases that are emitted in the volcano, such as like carbon dioxide, may in longer time frame actually contribute towards a warming trend for that process. These are just some of the examples of the natural causes of climate change. So I want to slide down into the human causes here. The Intergovernmental Panel on Climate Change, they're known as IPCC. It's a group of scientists who issue comprehensive assessments on climate science. So according to the IPCC reports, we know that the humans are impacting the climate and has been very prevalent over the past 100 years. Any human activity that is resulting in greenhouse gas emissions in the atmosphere is categorized under this criteria. So some examples of human causes are energy production, fossil fuels, and fertilization of farmland, livestock production, and part of agriculture. So I mean, really everybody is part of releasing greenhouse gases into the atmosphere, and you can kind of see this process here on that. Also looking at different ways, the greenhouse gases, significant climate change can also be caused by changing the radiation balance of land. So if you go through and cut trees down, you're also, or if the sea ice melts, you're changing that radiation budget. So you're also causing issues with that and can lead to more radiation being absorbed by the ocean and could also cause warming for that as well. So you can kind of see that in this slide here. So the natural and human causes of climate change. So I want to dive into the greenhouse effect and what greenhouse gases are. All right, so the greenhouse effect, the Earth's atmosphere kind of acts like a greenhouse. So if you look at life on Earth, it depends on energy coming from the sun. Almost half of the Earth's energy coming from the sun passes through the air and clouds to the surface. That radiation can actually be absorbed by the land or plants or whatever that object or that radiation actually hits. And then that is actually re-emitted or re-emitted to the atmosphere based on long wave radiation or infrared heat. And an ordinary greenhouse keeps plants warm in the winter without using a heater, kind of like that. So the glass actually traps some of that heat from going and passing through the glass and going back out into the air. So it kind of helps that heat from escaping from that. So you can see that in this graphic here. But we do know that the greenhouse effect is actually a natural process that helps warm the Earth. Without the greenhouse effect, we would definitely not have enough heat to help sustain human life. And that's something that is extremely important. But most, not all, of the visible light passes through the greenhouse gases in the atmosphere. So you can see that on the chart here, that the graphic. So you see the solar radiation coming into the Earth, and it's either reflected or absorbed by the Earth, either land or water. And the absorbed light is emitted as infrared radiation and heat. Some of that infrared radiation gets trapped and absorbed by the greenhouse gases and emitted back toward the Earth, and that actually contributes to the warming of the Earth. So you can see we have naturally occurring greenhouse gases. This is that natural greenhouse effect that we're talking about. The one that we'll talk about next is where we start throwing in additional greenhouse gases to the system here. So you can see how the natural greenhouse effect and the human enhanced greenhouse effects kind of compare with each other. So as you increase that concentration of atmospheric greenhouse gases, that increases the amount of infrared radiation and heat emitted by the Earth that is absorbed by those greenhouse gases. So if they get absorbed and then gets re-emitted back towards the Earth, you're actually just reheating the Earth. And so you can see that. So take this for an example, okay? And it's not really talking about greenhouse gases, but if you have a clear sky day and you have you go into the night, you have the sun, completely sunny skies, and as the day progresses and go into the night, the temperature really falls overnight, right? If you don't have any clouds. But if you have an insulation layer, like with clouds coming in overnight, those clouds actually trap the heat and re-emits that radiation back towards the Earth. It actually helps keep it warmer compared to times when you don't have clouds. So that's another kind of way of looking at how that happens. But when you start adding more CO2, methane, nitrous oxide, less heat actually escapes into space, and it just kind of stays. So that kind of helps lead to that global warming aspect of everything. So for atmospheric gases, we do know that the Earth consists of a mixture of mainly nitrogen and oxygen gases in the atmosphere. These aren't necessarily greenhouse gases, but the atmosphere does contain a significantly smaller percentage of inactive gases like argon, neon, helium, hydrogen, and xenon. And you can see those as part of this graph, and several other gases that vary in concentration. So this is where you start talking about the greenhouse gases like the water vapor, carbon dioxide, methane, nitrous oxide, ozone, and the chlorofluorocarbons for that standpoint. So greenhouse gases do make up a very small amount of the atmospheric gases, but obviously human interaction is releasing additional greenhouse gases into the atmosphere. So there are various greenhouse gases. We've already mentioned several of them here. Water vapor is actually the most abundant greenhouse gas. So when you look at water vapor, as that increases as the Earth atmosphere warms, so there is a linkage between those two. Because of the increase, the possibility of clouds and precipitation also increase, and making these one of the most important feedback mechanisms to the greenhouse effect. So that's something that really kind of plays a role in that process. Carbon dioxide, that's released through natural processes and also such as like respiration, volcano eruptions, and also through the anthropogenic activities. And also if you have deforestation, land use changes, and burning of fossil fuels, and Hans will talk about the carbon cycle here in a few slides. But really kind of throwing off the whole budget of everything can really lead to warming as well. Methane is also a hydrocarbon gas that is produced through natural sources. So human activities, decomposition of waste in landfills, agriculture, if you have rice cultivation, ruminant digestion and manure management, some of those issues release methane. It's a much more active molecule than carbon dioxide, but it's actually smaller in quantities in the atmosphere. Nitrous oxide is also produced through soil cultivation practices. So when I did my master's, I looked at anhydrous ammonia applications and how denitrification released nitrous oxide into the atmosphere. And so taking a look at how Different agricultural practices do that. Nitrous oxide also gets released in the atmosphere from combustion processes and stuff like that as well. So that's something that plays into that. Fossil fuel combustion, as I had mentioned, nitric acid production, biomass burning, a lot of those different ways to actually serve as an emission source for nitrous oxide into the atmosphere. Chlorofluorocarbons, I don't really have this mentioned on the slide here, but these are also known as CFCs. They are considered a greenhouse gas, as these are basically a synthetic compound from industrial production, but these also contribute to the destruction of the ozone layer, which also kind of impacts that radiation budget for the Earth as well. So you can kind of read up on that more too as well. This slide shows the breakdown of greenhouse gases. We don't necessarily have water vapor associated with it, but as previously mentioned, carbon dioxide is the largest greenhouse gas that primarily comes from fossil fuel use, deforestation, decay of biomass, and you can see that here at that 17% there, the yellow. And then methane sources are the cows or ag livestock production. Wetlands, fluorinated greenhouse gases are also a family of the man-made gases that we talked about. So the hydrofluorocarbons, the HFCs, these are used in refrigerants or air conditioning and heat pump units for to try to help keep people cool. Blowing agents for foams and fire extinguishers and aerosols. Perfluorocarbons, the PFCs, these are also typically used in like electronics, cosmetics, and the pharmaceutical industry. These used to actually be in fire extinguishers, but they're not really as common anymore. Another one is the sulfur hexafluoride, so SF6. These are actually used as an insulating gas and also involved in the production of magnesium and aluminum. So we kind of see what the breakdowns of what the different greenhouse gases are and kind of where they come from. I just wanted to kind of show you, and this is the famous curve that everybody talks about when we're talking about climate change. But this is the atmospheric carbon dioxide at the Mauna Loa Observatory, and you got your parts per million on the y-axis there. So you can see since 1960 that there's a pretty dramatic increase in the amount of carbon dioxide that's been released into the atmosphere. And I actually looked May 2020, we are up to 417 parts per million of carbon dioxide into the atmosphere. Also, the monthly mean carbon dioxide at Mauna Loa is on this side, so you can see over the past 5 or 6 years here, you can see that overall concentrations are increasing, but there's also a pattern. It does vary over time with that. So I wanted to talk briefly about the breakdown of emissions per industry here. So you can see for U.S. emissions and then U.S. emissions by economic sector. So you can see the largest, again, I feel like I'm a broken record here, but carbon dioxide at 82%, methane at 9%, and nitrous oxide at 6%, and those fluorinated gases at 3%. The U.S. emissions by economic sector, you can see here, electricity is at 32%, and talked about the coal on Tuesday and how a lot of energy production still involves the burning of coal. Transportation is actually at 28%, industry at 20%, and then commercial and residential still has a piece of the puzzle, so that 10%, and then agriculture is also represented by that 10% time frame, or that 10% level there. That was just kind of a brief review of what the greenhouse effect, greenhouse gases, and how that contributes to warming. And I think I'm going to go ahead and pass the torch to Hans Schmitz. Hans actually graduated the same program that I did, but just several years. I don't know exactly how many years before I did, but we both had the same academic advisor, and So I want to go ahead and pass the torch to Hans, and I think Hans will do a good job for us here. So Hans, go ahead and take on over.
Well, thank you, Austin. I appreciate that. So I'm going to take over and just get into the carbon cycle a little bit, maybe talk about a couple other things in the process. First thing with the carbon cycle, just like a nitrogen cycle, a water cycle, carbon also cycles in an environment. And what you can see there is you can have sources of carbon, you can have sinks of carbon, depending on the way in which the arrows are pointed in the graph there. So I won't read all those to you. You can take a look at it for just a second and get some idea that depending on land surface and what's going on the land surface, those can have a lot of effects on whether carbon is being absorbed into that surface or being emitted into the atmosphere. If we talk about human influence, you see there kind of a carbon budget more or less, and the units are many grams. So when you get that large of a size, you do tend to have some rounding errors that mean everything isn't going to exactly equal out. And when we were coming up with the dynamics of climate curriculum back in 2012 to 14, I want to say, we spent way too much time arguing about whether those numbers should equal out or not. So don't worry too much about that, but do notice that you've got red arrows there that give you some idea. Yes, natural carbon cycles are a majority of what you see in that budget, but the fossil fuel combustion and industrial processes is not insignificant, and neither is the changing land use. The dynamics of climate curriculum, which is kind of a middle school to high school curriculum that was developed using a National Science Foundation grant. So it's available at the Purdue Climate Change Research Center website. You go to the homepage, you click on for educators and then K through 12 teachers, and open access to that entire curriculum for any educator. There is what I call the dice game there, which is a pretty excellent way to show the carbon cycle in pre-industrial times and post-industrial times. You basically have one set of dice that you're going to set out at 6 or 8 different stations. And each station represents potential carbon source or an area where carbon would be. So you see on this slide fossil fuels and atmosphere. There's also deep ocean, shallow ocean, vegetation, and so forth and so on. And participants then start at one station, roll the dice, and they go wherever their piece of carbon goes. So as you can see for fossil fuels, for that station, pre-industrial revolution, if you were a fossil fuel, if you were a carbon in fossil fuel, you stayed there at all times. And then when we look at starting to burn coal and the other fossil fuels, post the Industrial Revolution, you get into the potential for you to go to the atmosphere, where you could then be rained down onto all different surfaces or end up any number of places. But at the end of 20 rolls or 25 rolls, you tally up, each student tallies up the stations they've been at and the number of times that they were there. And what you find in aggregate from the entire class is that before we started burning fossil fuels, the amount of carbon in fossil fuels was relatively stable. And after we started burning fossil fuels, the number of fossil fuel carbons decreased. So it's just one way to kind of explain the major difference there with fossil fuel combustion. Now, if we look at the energy budget as a whole, stepping back, not just from carbon, but going back towards the idea of the greenhouse effect, you see here we've got reflection and emission, and it all begins with incoming sunlight. And a majority of that incoming sunlight in this particular scenario is going to make it to the Earth's surface and be absorbed or reflected from the Earth's surface. It could also be reflected by the atmosphere and clouds or absorbed by the atmosphere and clouds. Once it hits that Earth's surface, now we're starting to deal with long wave radiation that over on the right side can be emitted from the Earth's surface and then absorbed by the atmosphere or emitted into space. And that's kind of the whole budget and the whole driver of climate beginning with sunlight and then the radiation defining exactly how warm or cool we stay. So if we change the Earth's surface, can we impact the absorption, reflection, and radiation of the sun's energy? Of course we can. No question. Depending on what that surface is, we can have radiation hitting water, which affects the amount of re-radiated long-wave radiation. We can have it hitting snow, which is going to vastly increase the amount reflected. But it's important to note that if we change or have an external forcing on one portion of the climate system, and here you see what I referred to in curriculum development as the climate pentagram, changing a land surface is then going to change vegetation, the atmosphere directly above that land surface, potential for ice formation or melt, and any nearby oceanic or water body. So one change in one dynamic of the climate system is going to then begin to alter the other portions of the climate system and cause corresponding responses. Okay, and we do need to get into the concept of albedo a little bit, which is defined here in a very scientific manner with a example, but the basic concept of albedo is the amount of reflected sunlight from that surface, or the amount of reflected radiation from that surface. So if you look at the chart there, fresh snow reflects a large amount of sunlight or radiation that hits it. On the converse end, water, when the sun is near its high point, or asphalt, has a very low amount of reflection, a very high amount of absorption of that sun's energy. So I do try, wherein the opportunity exists, to explain albedo, particularly to elementary or middle school students, in the following way. I will try to have them do some type of weather activity outside. And invariably, if you're in a school setting and you're outside, you're in some transition zone between a concrete or asphalt area and a grassy surface. So the weather activity that you do doesn't necessarily have to have anything to do with albedo, but you're going to have the kids sit on a sunny day in the grassy surface for some period of time, and you're going to ask them, how do you feel at the moment? And then during the activity, they're going to have to get up, they're going to have to move around, and you're going to sit them back down on an asphalt or a dark surface, and you're going to watch them become uncomfortable over 3 or 4 minutes. Likewise, when you're doing an outside activity with youth, particularly on a summer day, there will always be some wearing very dark colored shirts and some wearing very light colored shirts. And if the activity lasts long enough, you can really start to gauge the differences in those that are wearing different colors, different albedos of shirts. So we can change the Earth's energy budget. We can change it by changing the Earth's albedo, taking a native deciduous forest area and turning it into a city. That also changes the Earth's land surface We can change the land cover by taking a prairie area and planting row crops. It all changes the albedo a little bit, and we can enhance or detract from the greenhouse effect correspondingly. Generally speaking, humans have the tendency to change that albedo to absorb more radiation, darker surfaces, and as a result, we've got global average temperature increases, global warming. So if we look at another depiction of global warming, which is here the global mean temperature over the lands and the oceans, and we compare it to the average from 1901 to 2000, which is your horizontal line in the middle, you see that since we started having a lot of good temperature readings, a good network in around the 1880s to about 2010, there's the trend line rising. If we want to look at indicators of a warming world and how that looks, you see the black arrows indicating a decrease in glaciers, snow cover, and sea ice, and you see the white arrows indicating an increase in water vapor, the temperature over the oceans, the temperature over the land, sea level, and so forth. Now, as we start to segue into where this consensus on climate change comes from, we have to start looking at models. And herein lies the results of one model that looked at observations of global temperature over time and factored in only the natural factors in the green there, or the natural and human anthropogenic factors in the blue. And what you see is this model does have some variation and some amount of error. But if you look at the validation of the model, the verification of the model, the natural factors only included begins to significantly vary from the observations around 1975 or so. And as you run that model on through and include the human factors, it continues to have a little bit less error than natural factors only. So if we want to look at how we create consensus around climate change, that's where you start. You start creating models of predicted climatic change behaviors, and you start allowing them to verify over time and see if your hypotheses were correct. And in this case, this is the 2014 National Climate Assessment graph. It's a pretty understandable and telling model result here. We do know that if we just look at the last century, the warming we've observed compared to the warming in the past is unusual in its rapidity and the short amount of time in which it has occurred. Present conditions are outside the range of natural cycles that humans have experienced, and natural changes do continue to affect the climate today. As our models have verified, we can say that the warming of the last century is primarily human induced. And if we look at the experts, if we look at climate experts, this was back in 2010, you had 97 out of 100 that thought humans were changing global temperature. And that number remains to be 97. One recent study ended up with 100, but generally speaking, getting 100 people in a room to agree on something, doesn't matter what it is, virtually impossible. So 97 out of 100 is a pretty good consensus. If we look at some of the other organizations that agree with the consensus, you've got the U.S. Climate Change Science Program, the National Academy of Sciences, and National Academies of 32 other nations, probably more than that now. This was from a 2015 slide deck. Every major scientific organization whose members include climate scientists, more than 97% of climate researchers, these various companies and governmental units here, And then I did go ahead and follow up to confirm that this is still the case, but it is every major religious denomination with a climate change statement except the Southern Baptist Convention. That's still an exception. So as one example of climate change, a story that hits close to home for me. We start in 1988 with James Hanson testifying before Congress stating the quote on this slide. And the resulting effect of that helped tighten some restrictions on emissions in the Clean Air Act of 1990. And as a result of those restrictions, the National Trends Network and National Atmospheric Deposition Program started to observe that the amount of sulfur dioxide that was in rainwater was decreasing, and equally, the pH of rainwater was increasing. So I, as an elementary school student, know that at least 3 different times in science class had to learn something about acid rain. I have a 13-year-old at home, just finished up 7th grade, and I have asked him every year since around 2nd grade, has anybody told you anything about acid rain yet? This kid has never learned the first thing in school about acid rain because the pH of our rainfall has increased by over a point since I was going through elementary school. And that's an amazing example of how one particular human change, the restriction on emissions from large industrial plants, changed what's taught in schools, changed what we observed in the environment, and as a matter of fact, it changed agriculture, because in 2014, 2015, the Indiana corn specialist and soybean specialist began to find that the lack of acid rain, the lack of sulfur that was falling from the sky, was creating sulfur deficiencies in our corn and soybean crops in areas where the organic matter of the soils was not very high. So as a result, indirectly, of the Clean Air Act of 1990, farmers today are applying supplemental sulfur in the amount of 10 to 20 pounds to the acre. So in summary, climate is changing. There's consensus around this idea. Hopefully we've given you a little bit of a backgrounder on the greenhouse effect, the carbon cycle, and albedo. There are some sources here, and they'll be in the recording that's presented as well, if anybody would like to take a look at it. Next time, we'll be talking about historical observations and what they tell us about Indiana's climate with Beth Hall. Here is the virtual business card. And I will end on this before we get to questions. I am kind of proud of myself because I did not use the joke that I thought of like right before I started presenting, which is that albedo is not just the exclamation that the Pillsbury mascot would use when he's being outwitted. I'm very proud of myself for that. That's a horrible joke. No one should ever have to hear that joke. And I'm really glad that I didn't share. Okay. So if we get to questions from co-hosts, you got to be ready to unmute now. Questions from last time that we didn't get around to. We're getting around to it now. We apologize if your question was not addressed last time. It's going to be as soon as I can pull up this text box. From Russell, with the expected increased rainfall in Indiana, have you looked at the effect of that on Lake Michigan, which is already at record high levels?
So I can start talking about this. I guess the there are a lot of people who are interested in Lake Michigan lake levels naturally, and there's a lot of erosion going on right now around the edges of Lake Michigan. People are worried about structures, roads. It is really difficult to say what's going to happen to lake levels going forward. We do expect more rain in the winter and spring in this region every year going forward. That would suggest that the lake levels could get higher. On the other hand, we expect warmer summers, which would cause more evaporation. And also we expect warmer conditions in general year round, which would mean that there will be less time when the lake is covered with ice. If you have ice on the lake, that's going to reduce evaporation from the lake. If you don't have ice on the lake, then there's going to be more evaporation. And so nobody knows whether the increased evaporation in those shoulder seasons and during the summer is going to offset or more than offset the increased rain that we expect in the winter and spring. So it's a good question. A lot of people would love answers to that. We just don't know.
I did open up a poll for everybody to save you all from getting an email later if you'd like to fill that out. The next question from last time is from Kat. Many of our states have similar information, with individual extension educators doing climate outreach with little support. My question is, what gave your university in Indiana, a traditionally conservative state, the courage and resources to create a climate education center?
Sure, I'll take that as I'm the director of the Purdue Climate Change Research Center. I guess we had this center already. It's not focused entirely on education. Really, this center's been around since 2004, and it's really focused on catalyzing more and more relevant climate change research at Purdue. But we are also focused on outreach and helping that information get out to people who need it, people who can use it. And essentially, we saw a need for this, and we just decided to use our resources to make it happen. So I don't know that there was anything that made our state in particular do it. It was just that this seemed like something that would be useful for people, and we hoped, and so that's why we're doing what we're doing.
Okay, from Patrick. Question for a future session. Why shouldn't this be the session? Is there data on trends in average and peak wind velocities and events in Indiana? Interested in impacts on shoreline erosion on Northeast Indiana's lakes? Maybe one for Beth here.
All right. Well, it's a good question. There are several parameters out there that we are anxious to get more information on. Obviously, when we talk about climate change and global warming, temperature and precipitation are the most popular. And in my presentation, webinar 3 of this series on Tuesday, I'll go through kind of why that is. We actually have lots of data for temperature and precipitation. When it comes to these other parameters like winds, wind speed, coastal erosions, even humidity, sunshine, there simply has not been a very long record of that data, and the data is very sporadic. So, a sensor that's doing wind at one location based on just the terrain and influences around it could have a very different impact to a nearby station. So that's another challenge with wind, is it's highly variable, much like precipitation is, whereas temperature can be far more continuous. If you have enough points, you can make assumptions of what the temperature was in between. But wind is very difficult. With that being said, I will be showing some data, some information of changes in wind, peak winds, sustained winds in the webinar on Tuesday.
Okay. 2 more questions from the last one, and then I'm going to close the poll. From Karina. Can we make a Google Docs with links to all the resources in one place, like link to the slides, link to the speaker's emails, link to the report mentioned? That would make the data easier to use and also refer to others who aren't here down the line. So I'll start by saying that links to registration, links to recordings are all on the same site. And if we want to look at slide decks, we are currently sharing those on an as requested basis. Melissa, would it be relevant for us to go ahead and post those on the site as well?
We can certainly talk about posting those. Certainly right now, just send me an email and I'm happy to provide you with what I can. And yes, like Hans said, we do have the recordings available, and I do plan to post as a PDF any of the final resources slides that are part of the presentation as well. And it's very easy to put contact information and all of that. So I probably won't set up a Google Docs specifically, but we'll make sure that all of that information is on our registration page.
Thanks, Melissa. Last one from Marilyn. Coal, oil, and gas companies have trillions in reserves carried on their financial books today, not counting reserves they are adding each year. What fraction of these existing reserves can we afford to utilize and still stay within the 2 degrees Fahrenheit of warming?
I can say something about that. I don't know exactly what fraction of the stocks, I don't remember off the top of my head what fraction of the stocks we can use to stay with and still stay within 2 degrees. But I guess there are a few things that I would say. One is that any of the fuels that we burn will cause warming. 2 degrees is a bit of an arbitrary number. We want to ideally limit that warming as much as possible to minimize the risks of crossing a variety of possible tipping points and thresholds, none of which we really know the exact location of or timing of. It's all sort of a game of minimizing risk, really, and costs and benefits, we just don't know. Essentially, every day as we're continuing to emit greenhouse gases into the atmosphere that are going to be trapping heat for a long period of time, we are likely crossing some sort of threshold in the future because the gases that we're releasing are going to be warming the planet for so long. And we have a lot of warming that's already locked into place. So we don't know at any given moment what threshold, what tipping point we are causing to get past today that's actually not going to take place for another 30 years. But we are crossing those thresholds all the time. So, greenhouse gas release that we can avoid now is going to contribute to avoiding some of those tipping points in the future. So, so I guess it's just reflecting my perspective that there's not necessarily a specific target that we should be particularly worried about. We just have to be worrying about essentially minimizing our impacts, minimizing our emissions all the time, keeping them as low as possible.
Okay, now we had one question submitted via email, and I have been looking through the participant list and don't see that individual on today. So we'll get back to that individual via email later. I noticed that Jeff had been answering some questions in the chat. Do we have anything outstanding still in the chat as we do approach the top of the hour here?
So one of the questions asked, what was the dip in natural forces around 1995? So Hans, I'm guessing that was regarding the slide that had the human factors and the natural factors parsed out, overlaid with the observed temperatures. So what was the dip in natural factors around 1995?
Oh boy.
I answered that in the chat, actually.
Oh, you did? Good.
Yeah, so Mount Pinatubo erupted, and now I'm forgetting, I think it was 92, but it might have been late 91. That eruption was a really violent eruption that injected a lot of sulfur dioxide into the stratosphere where it could stay for a long period of time, and that led to a couple years of cooling after that. All the dips, all the significant dips that you see in the natural record are typically volcanic eruptions that are big enough to cause long-lived sort of elevation of sulfur dioxide contents in the atmosphere. And sulfur dioxide is, primarily in that case, just cooling the planet by reflecting incoming radiation from the sun.
What he said.
There's another question in the chat on that, just while I'm talking, that I might finish answering. It was on, can you explain the significance of methane increases and feedback on tundra thawing, leading to more methane release? So when we're warming the planet, the warming is happening fastest towards the poles, and particularly towards in the Arctic and boreal forests. And the main reason for this is that you're causing so much ice melting up at those high latitudes during the spring, and you're melting ice sooner in the spring, and it's icing up and snowing later in the fall. So there's more period of time when the albedo is lower, basically up there. Basically, more of the incoming radiation is being absorbed, and so that helps warm the planet. That amplifies the amount of warming that you get up at those high latitudes. And so we're seeing that part of the planet warm much faster. That's also the part of the planet where we have permafrost and really high carbon soils. So very, peaty soils with lots of organic matter in them. As those soils warm up, that carbon becomes vulnerable to decomposition. And that decomposition can happen either turning carbon into carbon dioxide when the soils aren't super wet, or if the soils are saturated with water, it can be turned into methane. Both of those are going to cause positive feedbacks to the warming. Whether it's released as CO2 or methane, you're going to get a little bit of warming, suddenly leading to more long-term warming from that carbon now being in the atmosphere instead of locked away in the permafrost. If it's methane, that warming is going to be stronger sooner, because methane has, much, depending on the time frame, it's about 20 to 30 times stronger in terms of its warming effects than carbon dioxide. But the carbon dioxide will stay in the atmosphere for longer. You may from lakes, from the permafrost melting below lakes, you may get more methane. From permafrost melting below drier you may get more CO2, but either way, it has the potential to be a really strong positive feedback to climate change. We don't know exactly how strong. That's still a bit of a question in the scientific circles, but there's a lot of research going on that right now.
Thanks, everyone.
Thanks, folks.